We'll start with the second to last talk by Sarah Williamson, who's a PhD student in UT Austin at University of Texas in Austin, this way around. And we're going to hear a bit more about differentiable ocean models with Julia.
Hi, my name is Sarah. I'm a graduate student at the University of Texas at Austin. I'm going to switch a little bit and talk more about kind of a method with the Earth system models in Julia, and we're going to talk about differentiable oceans specifically. This is work that I've done as part of the DJ for Earth collaboration, which means that I have a bunch of other lovely researchers to thank for making this possible. And their names are all up here. The first part of my talk will be a bit more on the mathy technical side, like the methods that we're using. And then the second half will be how we're doing this in Julia. So let's get started. So why are we interested in differentiable ocean models? Our overarching major goal is something called adjointable models, which basically means I want to do something called the adjoint method. And for adjoints, which we should think of as gradients, we need differentiable code, and this is where Julia is going to come in. The adjoint method allows for problems such as data assimilation and sensitivity analysis, or furthermore, integration with machine learning. Basically, in a neural net, you need gradients. The adjoint method can help you compute those. So we'll talk a bit about, first, what is the adjoint method? Overall, it can be viewed as a nifty way to compute gradients. The general framework is that we define a cost function. This is any scalar valued function that depends on the model we're interested in. The second step would be to integrate the model forwards. 3 is run the backwards problem. We'll talk a bit about what this means in a sec. And then the last step of the adjoint method is to compute gradients. And so how do we do this? With our predefined cost function J, we're going to define a Lagrangian L, where L is going to be the difference between my cost function and the sum over the steps that I've integrated of mu of t transpose, where here mu is my Lagrange multiplier. We can also think of mu as the adjoint variable. You might hear me use this phrase instead. Times the difference between x of t, where x is the state of my system, minus L of x of t minus delta t. L here is it's a time step. So L is going to propagate my state x of t to x of t plus delta t. So just one step of the model. And then to find the gradient, we're going to minimize L, and going back to calculus means we take derivatives of L and we set them equal to 0. This leads to something called the adjoint equations. The first equation I have is the derivative of L with respect to my adjoint variable. Setting this equal to 0 and solving for my state x of t returns to me my model equation, so this is really just the integrator. The second adjoint equation I have is the derivative of L with respect to the final state of the system. Setting this equal to 0 defines for me an initial adjoint variable. I say initial loosely because this adjoint variable is technically defined the final time step. And so this is going to start for us this backwards problem. The final adjoint equation I have is a relationship between mu of t and mu of t plus delta t. And so this is going to be how we actually propagate these adjoint variables backwards in time. So this is the backwards problem of the adjoint method. I have boxed a term in equation 3, and I've boxed this because this is kind of like the important gradient. So this is the derivative of my forward step with respect to my state, acting on a prior adjoint variable, or an adjoint variable one step in the future. And computing this gradient by hand is very cumbersome, and this is explicitly where automatic differentiation is going to come in. Okay. So next we can talk about a little bit of the different ways that adjoints can be used. So obviously we can always define different cost functions. For example, your cost function is any scalar valued quantity. It could be a measure of energy, for example, and this can help you answer questions such as, how would the energy at my final state change were I to change the initial conditions of my model? We can also look at cost functions that are model data misfits, and this would be for something like data assimilation. Here I have a J, which is the squared L2 norm of a state x of tk minus d of tk. X is the state as I've computed it through my model equations. D is maybe high resolution data that you've gotten through other means. We can also ask different sensitivity questions with the adjoint method. So we can look at sensitivities with respect to states. This would be like a derivative of my cost function with respect to a state, and this is explicitly just my adjoint variable. So that kind of helps you get a little bit of physical meaning to these kind of abstract arrays. We can also look at sensitivities with respect to model parameters. This would be like dj to d alpha for some constant alpha in the model equations. For example, how does my final state depend explicitly on this parameter alpha? The final example I have is a combination of 2 and 3, and this would be for parameter estimation. So let's say I have some physical system that I'm interested in, and there's a parameter in the system that I'm uncertain about, but I have a prediction. However, I also have high resolution data. I can define a cost function that's a model data misfit and use the adjoint method to compute a derivative of this cost function with respect to my uncertain parameter. And then we use this gradient in our favorite gradient-based optimization scheme to hopefully improve what we predict the parameter to be. And so this is by no means an exhaustive list. This is just a kind of a sample way that the adjoint method can be used in practice. And so there's one small hiccup in all of this. We notice that this important gradient, I've boxed it here again, this derivative of my forward step with respect to the state, actually requires knowledge of the state x of t. I should put an asterisk here because if L was a linear step, then I no longer require knowledge of my state. The derivative would just be a constant. However, in most instances, L is highly nonlinear. So I'm going to need to know what x of t is to actually compute the adjoint variables. This dependence is independent of my choice of J. And for large ocean models or most Earth system models in general, storing the state at every time step just isn't possible. You'll very quickly run out of memory and you won't be able to do it. However, there is another handy way that we approach this problem, and it's with something called checkpointing. So checkpointing is kind of this workaround for the state dependence and the gradients. It does come at a trade-off. I will be using a lot less memory, so I'll be able to compute these variables, but I'm going to be doing a lot more computations. And so I have here an example with 8 checkpoints. So let's say I have some initial condition to my system. It's x of t naught. And I'm going to integrate my model forward. And as I integrate the model forward, I'm going to save the states x of t1, x of t2, et cetera, up until x of tf. These saved states of memory are now called my checkpoints. And once I get to the final state, I'm free to compute my initial adjoint variable because this lives at the final time. And then we can go back to the last saved checkpoint. In this case, it's x of t6. And we can reintegrate the states between x of t6 and x of tf. Okay, and so once we have those states reintegrated, we're free to backpropagate our adjoint variable to the last checkpoint at t6, throw away the states that we no longer need in memory, and then we can rinse and repeat the process moving all the way back. So at the end of the day, we'll have done the forward problem twice, but we'll have done it with the ability to compute all of these adjoint variables. And so this is how we get around the state dependence. And so kind of moving into the second bit of the presentation, summarizing why are we so interested in adjoints. One of the first reasons is that finite difference gradient calculations don't converge numerically. And so the result from the adjoint method is theoretically an exact gradient. I say theoretically because there's always numerical error, but this means that it could help you with your optimization scheme to have a more accurate gradient. And then the adjoint method also really shines in instances where the model of interest is very expensive to compute alongside a high-dimensional control space. What do I mean by this? I mean that my forward run is very computationally intensive, and the derivative that I want to compute could say be with respect to an initial condition. This initial condition can live on a 100 by 100 grid, which would be theoretically 100 squared different finite difference gradient calculations that I would need to do. So in instances like this, the adjoint method will compute all of those for us simultaneously, and it really comes in handy. And then why do we want to do this with automatic differentiation? So as my model code grows and changes, my AD tool will stay the same, and there's never any need to adjust my derivative calculation. So for example, I could theoretically write down my adjoint code by hand, but as soon as I change something about the model, that little tiny change can propagate through my derivative calculation, and that opens up a lot of room for error. With automatic differentiation, I don't need to worry about this. Okay. So why do we want to do this in Julia? So one of the first reasons, as we've seen multiple talks on, there's a new Earth system model currently being built in Julia. This is the Klima model, and I'm specifically very interested in their ocean component, Oceananigans.jl. So with that being built, there's never a better time to differentiate the model. Julia also has the potential to be faster than prior languages, as we've seen. Julia already contains for me 2 key packages for the adjoint method. We'll see what those are on the next slide. And prior packages like these were largely in Fortran. They are potentially closed source, which is not very helpful to people who want to build their own Earth system model or differentiate their own Earth system model. So the 2 packages that we're using for the adjoint method are Enzyme.jl and checkpointing.jl. So Enzyme is an open source automatic differentiation tool, and this generates and compiles the adjoint code for us, which is really, really handy. This was developed by Moses and Shiravi, and you can scan that QR code for a paper by them that goes more into depth on the package. And in general, computing the derivative of the forward step with respect to the state by hand is very cumbersome. Enzyme does this for us very cheaply, which is great. Checkpointing.jl is a little bit confusing because the name of the package is the name of the method, but capital C is the package, lowercase c is the method. And checkpointing.jl just implements checkpointing schemes for us, and it's already doing this using Enzyme for the differentiation. So this is actually being developed explicitly for the DJ for Earth collaboration by Sri Hari Krishna and Michelle Shannon. You can scan the lower right QR code for our paper by Shannon et al. That goes more into depth on the package itself. And so with these two, we can put it all together into a current working example. I wrote a barotropic gyre model in Julia. This is, you should think about it as just like a rectangle of fluid. There's wind flowing on the fluid. This generates circulation. There are three main unknowns in the system. It's u, v, and eta. U and v are the x and y components of my velocity vector, respectively. Eta is the displacement from the at-rest layer of fluid that is the model. This is a fully explicit solver with RK4 time stepping, and it was adapted from a Python model written by Milan Klöwer, so thank you to him. And then here I have a snapshot of the x component of the velocity as I was integrating. So the sample sensitivity I'm going to compute with the adjoint method is, let's say I want to know how sensitive the spatially averaged energy at the final time is to my initial displacement field eta. My cost function is then the sum over u squared and v squared divided by the number of cells in the x direction times the number of cells in the y direction. I'm going to try to compute dj to d eta of t naught. I also note that checkpointing is needed in addition to enzyme, so even though this is by no means a full-fledged ocean model, I'm already unable to save all of my states in memory. I absolutely need to use checkpointing. The model was spun up for 10 years, and the sensitivity was for a 1-year integration beyond those 10 years. A full working example is in Julia on the DJ for Earth repo, and then here I have a snapshot of the energy density during that 1-year integration. And so what does enzyme and checkpointing give us? It gives us a nice little sensitivity video. So this is moving backwards in time, the derivative of the spatially averaged final energy to eta of t. So they're kind of, each frame is just a different adjoint field. And as we move backwards in time, we see the sensitivity. So this is kind of the goal. And so in summary, Julia just holds a lot of potential for adjointable Earth system models. Like as we've seen, Julia holds a lot of potential for Earth system models in general. Being able to differentiate them and do sensitivity analysis or data assimilation with the adjoint method would just be an added bonus. Enzyme and checkpointing are both open source Julia packages that facilitate fast and efficient generation of my adjoint code. So it's really great. I don't need to write my adjoint code by hand. I get to do it with these packages that are freely available to everyone. Some of the next steps that we'd really like to see is one day we'd really like Oceananigans.jl to work with enzyme for gradient calculations. So this would open up something like the ECHO model that exists in Fortran. So we heard Greg Wagner talk about MIT GCM. The MIT GCM is one of the few models that actually has an adjoint model with it, and that's the ECHO project. And so we have the potential to build an adjoint model also in Julia, but with Oceananigans, and that would be a very exciting prospect. And then here is the actual sensitivity field that is like the final frame in that video. But yeah, so that's what I have, and thank you.
Any questions?
So we're hearing about a lot of models written in other languages being rewritten in Julia. Are the users of the original models in the other languages, how are they taking advantage of the Julia developments? Are they plugging in the Julia packages into their other language codes, or are they switching to Julia?
I don't think anyone is switching to Julia. Like, I don't think the MIT GCM is going to go away. I think that people are kind of using both, which I think is probably better. So you have two options. And the people who wrote the MIT GCM are, I think, some of them are also working on Oceananigans. I want to say Chris Hill was part of the MIT GCM build. Yeah. So I hope that answers your question.
Great talk, by the way. So with the checkpointing, I was wondering if you found like a sweet spot for like the number of time steps that you group into the checkpoint, and if there's any values that are too large or too small, and you know how you went about that.
So that's actually a great question. So if you choose too few checkpoints, you would also end up running into issues. If you also use too many, you're going to be doing a lot more work, or you're saving too much in memory. I did find that like the square root of the number of time steps is roughly the number of checkpoints that you want to choose. I don't have the math on me for how I found this, but that's about how I was choosing the number of checkpoints.
Follow-up question, but that probably depends on the non-linearity in your system, right?
It depends
so like
on
a more turbulent system with like like more turbulent in the same number of time steps, you would probably need to shorten the number of checkpoints, right? Is that conceptually, do I understand this conceptually correct?
Sorry. No, I was just looking at the size of the actual state. So like you can use Julia to compute how much memory the structure with the variables being checkpointed is, and basing that off of how much my computer has. And that's, yeah.
Yeah, it's more just
I guess, I mean, it depends a bit. So if you assume each time step is kind of self-similar, like you do the same amount of computation each time step, then really it's just, there is some math analysis that suggests some binomial kind of formula is kind of what you use for kind of a hierarchy of checkpoint. I think you only have one level of checkpointing, yeah. In the more general case, you kind of end up with hierarchies of checkpoints, and then there is some optimal thing that is based on some binomial math distribution thing. But yeah, the actual assuming each time step is kind of the same, then the complexity of the time step kind of drops out when you do that.
I don't want to
No,
you go first then.
Are there any difficulties with external, like if we say user sets up something that involves an external package that's not a Julia package, like would you be able to handle that, or is that kind of too futuristic?
I feel like that's up to Enzyme. Theoretically, Enzyme should work with any Julia package at least. In practice, you might run into more bugs. Yeah.
Hey, yeah, nice presentation. So I guess I'm one of those people that uses MTGCM on its adjoint. So I'm kind of looking at a future where maybe we can use Oceananigans on its adjoint for things like echo. And so my question is kind of how far along in that process are we, and kind of what's the time horizon, I guess?
I think we're doing okay. Yeah, maybe Chris Hill.
It's like next year?
So there are a few features in the kind of fusion of how kernel abstractions and GPUs have been used in Oceananigans that Enzyme needed some work to actually be able to parse that or deal with those correctly. Billy actually fixed most of that about 3 weeks ago, and so we're just doing some tests to see whether, in which case, we will have a kind of equivalent of what Sarah's doing fairly soon that is actually in Oceananigans, but it needed some bits in Enzyme to. So what Sarah's example is, running on CPUs and not using kind of some of the packages that we use in Oceananigans. So it was easier for Enzyme to work with that.
One last question, maybe? Oh, okay.
In this morning's keynote, Chris Rakoukas talked about how symbolic math is being expressed in code and vice versa in automatic differentiation. I think your presentation had the most equations that I've seen. So I'd like to ask you, how do you see these developments in symbolic math and computation affecting academics and research in mathematics and computation? And do you see Julia having a prominent role in that?
Oh my goodness. So I feel like what Chris showed when he showed the derivative code was explicitly him showing the adjoint code. I'm sorry. In terms of where Julia can take this, is that what you mean?
It sounds like a big new development.
Oh, no. I mean, I feel like symbolic math has been around for a very long time because the ECHO project was started in like the 90s, I want to say. And so the idea of the adjoint method and adjoint code in general is not a new concept. It's fairly old, actually. And what Chris was talking about with symbolic math, I feel like is just very similar ideas, so to speak. I hope that helps answer a little bit.
But do you feel like Julia is enabling further advancements on that in ways other languages haven't?
I think it's pretty exciting that Julia is as fast as it is and that it has the potential to do these automatic differentiation capabilities. Like, running the MIT GCM's ECHO project is a very large endeavor. Like it's in Fortran, you need to set up your model correctly, and generating the adjoint code is hard. The fact that this could be like you download Oceananigans on your laptop and you could potentially differentiate it all on your laptop is I think it's very exciting for Julia. Yeah.
Amazing. Then I would say we thank Sarah again